Hello and welcome. I'm Bill Wake. We're here working on an Elm interpreter. We're kind of in the middle somewhere. And what we're up to is trying to go from a spike that we did yesterday to getting operators as true functions. So that's a characteristic of Elm, not shared by every language for sure. So you might be used to 3 plus 4 as the way you write an arithmetic expression. Elm also provides an operator called parenthesis plus, I don't know what they call it. I keep trying to call it prefix plus, but it's left parent plus right parent. And you can wrap any operator in parentheses like that, and you have a function now. So this is a function of 2 arguments, plus prefix plus of 3, 4 is the same as 3 plus 4. Modulo parentheses and whatnot, but if that's the only expression you got. Now, it's a true operator, or I'm sorry, a true function as well. And so in Elm, that means you can have currying. In other words, turn a function of multiple arguments into a function of 1 argument. So here on the bottom, you see plus 3, all parenthesized. The result of that is a function of 1 argument that is really a 3 plus x function. And if you continue on and pass in 4, you get 3 plus 4 substituted in. So every Elm function works this way. We have to make sure our operators do as well. What we did last time was basically a spike. It originally started out as like, oh, we're going to implement this, and then kind of devolved from there. But we found a bunch of things on the way, and my hope is we can do the real implementation, kind of migrate from the spike to production code today. So we took a little list of things to do. One is we have a closure function call that we used for sort of an early proof of concept of actually evaluating functions. That class is no longer used. We'll delete it. Another thing we did is we have this method apply, and it's in closure right now, but lambda expressions are the things that actually apply functions to arguments. So we wanted to pull that back over to there. We added a primitive, which is a subclass, and I believe we left it as lambda expression. I bounced back and forth between closure and lambda expression. And then we have a curry function. So a curry function, you can write one of these. It turns a function of multiple arguments into a function of 1 argument. Now in our case, we're kind of moving between domains. So our expression domain is where our results are, like integer values and float values. And our primitives, which are functions, are also going to be in that domain as expressions. So like lambda expressions. And so if you give this curry function another function, a function of 2 arguments, and it configures it so it's really a function of 1 argument returning a function of another argument. And you can generalize this to n arguments, I guess, but we mostly need the case for 2 arguments right now. And so what you're going to do is you're going to call curry of sum, for example. And if you look at sum, well, it takes an expression, 2 expressions in, and produces an expression out. And at the bottom, we want it to just be x plus y. But we're going to have to convert from expressions, make sure the types are compatible, and other stuff. But once we had it, we'll somewhere compute x plus y and then wrap that back up and put it in the return value. That's kind of what we have now. And in our spike, we just returned 42 and maybe changed it to 21 at the last minute to kind of make sure it was really bubbling through. All right, so let's see. And I did not start the tests, so let me do that. All right, so our plan of action is we're going to walk through all the places where we have changes and make sure we understand what to do, and then revert it and start mostly over. Okay. We'll let that test for a while. We can look around while it's doing that. Okay, so here's the functions we have changed. Closure's got some modest changes. If you remember, this is the one where we pulled the apply function from closure back to lambda. And the reason I could see that, it's probably worth going into. Um, we have, what is it working with? Well, it's working with the symbol table, and it's working with name, and it gets an argument. So basically, apply the your function with this argument in the context of this symbol table. And so name and expression are the things that the lambda expression owns. And I know that because I have two little helper functions up here. Let's see if I can move this down a bit, I guess. Okay, so the name function says go to lambda.name, and the expression says go to lambda.expression. And we know the lambda because when you created the closure, you passed a lambda in. A closure is a symbol table plus the lambda itself. Okay, and so what we have now, we just completely moved that over. We did it in two steps, but we moved it over now to lambda expression. Spinny beach ball. Okay, appreciate you staying around if you did. All right. That is... Okay, there it goes. All right, so we left off. We started looking at lambda expressions, and let's see, what do we got going on? There's initialization. That seems okay. EQ, and here's the apply function. So we left it calling the closure for evaluate, because closure is the thing that knows how to dig up functions and do them, but it's not calling evaluate. I don't know. It seems a little weird to me. But at any rate, you can see we move the apply over. Now name is the name right out of the lambda expression, and so is expression. Okay. And that's a feature envy kind of thing. So we had a class that was reaching over into lambda expression, pulling out the name, pulling out the expression, doing some work with it. And it's like, no, the expression should do its own work. Expression evaluate, that makes sense. Okay, so that's a definite improvement. Let's see, do I have my, yeah. Okay, apply from closure to lambda expression. Yes, we also introduced this primitive. Okay, and that's not starting very well, is it? Very slow. Primitive. Okay, lots of stuff in here. I don't know what that diff is. Maybe it's matching up the new file to the old file or something. Primitive was new. Okay, we created that as a new type of thing. So a primitive is kind of like a lambda expression. It's an expression going to an expression. So it's a functional kind of type. The function that it's going to have is going to be an expression goes to expression function. Okay, and that's okay. I mean, that's how we're going to get our primitives in. So we're going to make native functions in Swift that handle things like plus, and then we're going to call them from here and sort of fool the system into thinking it's a lambda expression. I mean, it is. It's just crossing that boundary over into the Swift side. Equality, we just kind of blew by. I don't know if it makes sense to test these or not. I don't see us wanting to test for equality, really. Okay, and evaluate it. Well, just like, I think just like lambda expression, actually. Create a closure with context and self. Primitive closure context self. So that override was not needed. And then it gets its own evaluate. Okay, and its own apply. It's got the symbol table. It's very similar. But instead of expression.evaluate, we just call primitive with the argument. Okay, so it's the same up to here. Then we call primitive with an argument, and then we decide, are you returning a function or are you returning a primitive, a value? If you're returning another primitive, then we're going to want to repeat and evaluate that, and it'll come back in here. And if I go back to, let's go back to that curry function here. That's the thing taking a two expression, a two argument function and returning a value. And you can see here, we see the two primitives. So the first primitive gets called with x. That makes it a function of x. And it's going to return a function that's a function of y. And that's why we have that little dance going on. And that might be worth saving. Let's just pull it over as example code, I guess. I don't mind doing that from a spike. I don't want to just leave it there, but I'm willing to do this. Okay. That's the new primitive. And let's see what else we got. Interpreter. Okay, so interpreter, this is where we put the curry function and the sum, and then a failed attempt to do plus and plus one. Although that sort of could work. So you can see I tried to make my plus function. I turned it into a function of one argument. Lambda expression something goes to primitive interpreter of plus. But this curry function was a more generic way to do it. So we didn't pursue this stuff at all beyond some early attempt. But yeah, you can see the 21. So we changed it and proved that it was working. All right, now we got some failures. Well, what else we got? Interpreter. Anything else in here? Somewhere we call curry. There it is. Okay, so in the initializer, we said, hey, you should add this to your symbol table. Here's a predefined function from the system itself, the system being the underlying Swift part. If you see parenthesis plus parenthesis as a function name, we're sort of making it be one, then you should return the curried sum function. And nothing else changes in here. Okay. Anything else? A little bit of tests. We wanted to check that this function 1 plus 2 equals 3. That's probably harmless enough. Save myself a little typing. Okay. Now, what was the failure? Hopefully it's just that one test. And it should be coming back 21 instead of 3. So we're convinced that our value bubbled its way up through the plus function, through the primitives, through the closures, through the lambdas, and ends up, getting interpreted as a result. Okay. I'm putting off the moment of trauma here. All right, so can I do this in one place? Okay, and this, we know we want to delete that. Delete. Okay. Now, what else we got? I guess I want to delete these discard changes. Discard changes. Okay. What's our diff? closure function call is gone. Tests are gone. Yep. Okay. So I should be able to run tests all red. I'm sorry, all green. Turn that off. Okay. And I guess I'm making my first change because closure function call is gone. I assume it was really there if I'd dropped the source control on these first. I don't know why doing it at the top level doesn't take care of everything from there down. That's kind of annoying. More than kind of. All right. Whew. Okay. So closure function call is gone. Let's commit that. Okay, I'm going to clean out the view here. All right. So, what's a good way to start this? Well, I don't think there would be anything wrong with starting with that curry function and some, at least the sum function. Now, where that should go is a question. In Elm, where they switch things into JavaScript, they call it native. I don't know. Can it go on primitive, maybe? So this would make primitive grow for all those things. That seems off to me. Let's maybe a class primitives, primitive functions. Okay. All right. So it's going to live in the interpreter. All right. So where am I not on the? Okay. I don't know what happened there. All right. Let's add the test down here. And it's a new file. Using John Reed's little test suite generator. And this is annoying. It's an example of one of those things that seems weird and you can't tell because I've upgraded Xcode once in there and simulators a couple times, I think. But the fact is, a month ago, I was not having that problem. Okay, primitive tests. And he provides a test 0 kind of thing, which we will get rid of here shortly. Okay. All right. So let's test the sum primitive. And I think, well, we know the heart of it is this x plus y, but we got expressions. Oh, let's see. Now, one thing we haven't quite dealt with, and I don't know what. Let me kick this off. All right, we'll get our little Chiron back. And we can do the REPL. So if I do plus, what does it tell me? Function of number to number to number. Okay, and if I do plus 3, it's still a function of number. If I do plus 3.0, it's a float to float. Okay, so that tells me I have to take into account the types. I don't know a good way to do that. Probably there's something we should... Well, I talked about trees yesterday in my blog article, and one of the places I mentioned was compilers. Many functions on trees evaluate from the bottom up. So you want the weight, you take the sum of the weights of the leaves and you add them up, and that's the sum of the weight of the interior nodes, and you continue that process, and then the weight of the root is the weight of the whole thing. Perfectly good use of a tree. Another set of tree things goes the other way down. So imagine you're writing in Microsoft Word and you've got a document style, and maybe you can set up a section style and a paragraph style and a character style. And as you get the tree of the document, sort of the outline, but down to all the way down, when you say, I want to put this character in, what font does it have? That's assigned going down, as it were. And our data types kind of want to go both ways. So when I do plus of 3 and 4.0, something, what's the type of the result? Well, it needs to be float. And so somewhere we have a big case statement, basically, or if statements that say, if you mix an int, if you mix a number with a float, the result is a float. And so the type of plus 3, 4.0 is a float up there on the plus node. Now, and you can keep bubbling it up, of course. But when we want to use this, it would sure be nice if both those were floats instead. So we'd like to push stuff back down. So knowing that the plus node is a float, we want to push down to the children and tell them, you should make sure you're a float. And it would be nice to have something that automatically converted so we knew which type we had and it was okay. We don't have that now. And, I'm not totally sure it's the right thing to do. It's just something that compilers do sometimes. So I'm going to make our sum function smart enough to deal with the combinations of types. And that's implying that we're going to have a number of cases involved. Now, another possibility is, and I'm not sure based on this if this is what happens, but you could, and I don't know if Elm does it or not, you could define different functions for float plus float and int plus int and number plus number or something like that. Again, I'm not quite sure what Elm does in this case, but I could imagine having a sum of integer values and a sum of float values, Okay, it complicates our tests and it complicates our life. Okay, so we are going, the thing we're going to call at some point is primitive functions dot sum of x and y. And we're going to get a result. And we're going to say assert that. Let's take integer. Let's take result should be equal to integer value of 3. Okay, so that tells me x is an integer value of 3 and y is an integer value of, oh, sorry, that should be 1 and 2. And its type is integer value. Type dot. If I picked the one type we don't support yet, I have. Let's try. Well, we had Elm-21-036. It stays number. Okay, so I guess the type is number, and that's the default. So we'll just let that go. Okay. Primitive functions we haven't written yet. X equals 1, y equals 2. Sum of x, y is 3. All right, that seems reasonable. Primitive functions, we're going to define that. Put that file in. A new file. It's just a Swift file. Let's call it P to stop the madness there. Okay. Primitive functions. Okay. All right. That should be fine, and we need sum. And that's one we kind of know what we want. Something like this. All right, x is an expression, y is an expression, and we want to basically return x plus y. Okay, and I'm going to well, we're going to fail first, so let's just undo a little. Okay. Let's get our failing test. So red then green, so we're going to try for red. Good, 42 is not equal to 3. All right. So I'm going to say let x equal x as integer value, y equals y as integer value, we'll find integer value in here. I think does it give us an access or just value? X dot value. I guess I can do it like this. If let y space that out a little. All right, so we're going to say if both expressions are integer values, return integer value x plus y, which defaults to type number. And that's legit. Okay, so I'm going to run tests, and I expect them to pass. Now, we haven't worried about overflow and stuff like that. I don't know what Elm does. I'm not sure if that's sort of the interesting part to me. Let's go. To expected value int integer value Oh, x dot value. All right. I'm not going to worry about overflow because I haven't decided if I am gonna worry about it yet. I don't know what they do in Elm, but I'm not thinking this project is like get every aspect of Elm implemented. It's more just like let me explore the key issues in doing that, and hopefully I have something that will execute stuff that looks like Elm, but I'm not trying to hit every boundary. You definitely could, though. I mean, you could catch the exception here and go on like that. All right, now let's handle um this thing needs to handle floats as well. Okay. And well, can I inline this? Am I readable enough if I do that? I think so. Okay, so create two integer values, add them, expect the result. I feel like that's all right. Okay, now let's do two floats. Maybe if either is float. So some primitive float plus int. Okay, so this is a float value, 1.0, plus an int value, 2, and we expect a float value, 3.0. Let me mix these up just a little. It's just kind of a good thing to change up the values you use. So you're just ensuring you don't mix things up. You're ensuring you haven't hit a weird case. Yeah, I think this is probably good. All right, and this will fail. Okay, and it should fail because of a conversion thing. 42 is not equal to 7, so it hit our bottom case. All right, so got a failing test. It's time for a break. So let's take a couple minutes, and we'll come back, get this sum function working, see if we can find a way to generalize the pattern of how it works. I don't relish doing these computations for every single helper function we put in, so we'll find a way to be better than that. Okay, 2 minutes, maybe 3 tops. All right, so we want to make this thing pass. We got primitive functions. The sum, if they're both integer values, then we're good. Okay. What if one of them is not? If I don't know. We'll definitely work on this code. Okay, if x is an integer value, whoops, I guess I got to deal with it here. Else, if let y equals y as float value. Okay, so if we have two integers, we just return it. If the first one's an integer and the second one's a float, we return a float value. And we need to get x dot value. Well, what does x have? X dot, I thought it had a float value on it or something. To float. Cast new type. No, that's not helpful. Okay, well, we're going to take x dot value. we're mixing the types. It's actually legit. It's a pity we can't do this in one if statement, but we sort of proved that yesterday. All right, so I think this will work. Int to expected target double fix. Okay, got to be more explicit here. What happened? Is it 42? Oh, I did the wrong case, didn't I? We said X was a float. Let me, well, let's fix it. So else if, how do I want to do this? Well, we have to get X in there. If X equals X as float value. And Y is an int value. Then we got to do float of X dot value plus double of Y dot value. That is a constant. Oh. Float value? Don't you hate that one? It's not as easy as you thought. Okay, there's value. Oh, I'm missing a brace. Okay, good. Now we pass. All right. Okay, so we got these combinations going, right? I mean, if now we want to deal with X is a float value, Y is an integer. Well, what if they're both floats? Let's put all the tests in. Okay, so if this will be int plus float. Okay, so this one's the int value. 2.02. Float value 4.0. Okay, so we got int plus float. Okay, we got fell through. So int plus float, that's this branch now. Let y equals y as float value. Return float value. So we got x dot value is an integer. So we need a double here. Plus y dot value. It's a float, so that's okay. That should pass. Else. That should pass. Okay. All right. So it's all buried in here, but let's see. We got integer plus float, float plus integer. We need float plus float. Okay, get that fourth test. Now, in general, you can't compare floats for equality, but if I know that there are small integers like this, it's okay. And I'm going to trust that if it was 26.5 or 26.1 to pick something that can't be represented exactly, it'll still work. You could beat me up for that, I guess. Okay. So float plus float. And the expected value. Okay. And then don't know why that didn't. I must have grabbed it wrong. Okay. We expect it to fail with 42 as the answer. I guess we've done that enough to know. Yep. Okay. Now, this case as integer value, no. Well, if let y equals y as float value. And now we can just say x dot value plus y dot value, kind of like that first case. And we expect to pass, although okay, I make the same mistake again. All right, now we've still got this last case, and that's what has to happen if something falls through because it's neither float nor int. Okay, so let's just make one of the cases just any arbitrary other type would do. I don't know if we have a good candidate. Well, error expression would be okay. We got integer value, float value, and then custom value. Custom value takes a little setup, so I'm going to let that go. So this last case, we're going to do an error case. And that's if the types completely don't match. Okay. Non-numeric. Okay, because that's what we care about. So we'll do a float plus an error expression. And I believe those take error messages. It doesn't matter which one, as long as you don't pick the one we're going to make the result be. Okay, and we'll just use nil because we don't care about location yet. All right, so we want to make sure that the result of that is error expression, error messages. Well, I'm doing this backwards, but error messages dot. Theoretically, it's a cannot happen. If we've done our type checking right, this should not be able to happen because we shouldn't let you even call a plus function on a random non-numeric type. All right, and then this, I lost this. So now the sum is going to be an error message, cannot happen, nil. Okay. And we're going to get 42. We hope. All right. Here we go. And I think I'll just take my expected. Okay. Now, these types, it's tricky. Well, okay. Now I have the logic pinned down. I can make some changes and try and clean this up. And I think what I want to do is peel off the case where both are integers. And if that's not the case, then convert everything to float and just deal with it as float. So I'm relying on my test to make this a safe move. Okay, so if x and y if they're both that, then we can return integer value of x dot value plus y dot value. That seems good. And that should pass our tests, even though this second half is redundant with it. Notice this is the only place that has that possibility. So we've covered that case. So I'm going to delete that. The only way to get through that path we've already blocked. So I think this is the case. This should be true. I'm trying to simplify things. Okay, now we've got the cases. Well, it would probably be better to start with float, but what I want to do is I want to convert I really want to convert my integers to floats, and then just do the addition with float value. Okay, so if and what I want to do is linearize my if tests instead of having this nested kind of thing. So I want to do something like if let x is x as integer value. What if I do that? It's an expression. Well, okay. If x is an integer value, then let's start it as x. If it's an integer value, I want to convert it. Okay, so I want to convert x to LHS float value. Okay, so if that has happened to me, I want to say LHS instead is a float value with the value of double x dot value. All right. So now I know LHS is a float. If it's not a float, can we fall through? What will happen? All right, let's can I do that? So expression, I'm surprised it lets me do this. I expected, yeah, a complaint that this must be an expression question mark. Okay, so if it's a float value, I'm going to use it as is. If it's an int value, I'm going to convert it. Now let's do the right hand side. Okay, if let y equals y as integer value, then the right hand side becomes a float value with double y dot value. Okay, so at this point I've got three possibilities. If x is a float value, then LHS is that value. If x is an int value, then it gets converted to a float value. Or x is neither value, then it gets converted to nil. Okay, because the question mark. So if possible, convert it, look at it as a float value. If not, change this to nil. Okay, so now I'm at the point where I have LHS is either a float value or nil, and RHS is either a float value or nil. So I feel comfortable saying if LHS is, I think I can do it that way, float value, and RHS is float value, we're going to do something, and that is this. Except it'll be LHS and RHS. Okay. And if it's not, if either one, maybe I can just say not equal nil. Yeah. Okay. So if we go through the path, it's either going to be a nil. Well, the income is either an int, a float, or something else. If it's a float, expression holds it. LHS holds it. If it's an int, LHS holds it. If it's something other than int or float, it comes up nil here. It doesn't qualify here, so it stays nil. Repeat that for RHS. You get to the end. If both of them are not nil, then you have two float values, and you can just add them. All right. Otherwise, return this. So I'm saying I should still be okay with all this stuff in here, but I can get rid of it. If it doesn't work, I'll just get rid of it and see, because there may be some path. But am I still not? Cannot convert value of string to expected argument double. LHS value of type expression. Okay, this should be float value. Value of optional type float value must be unwrapped. Yeah, I probably could. Well, let's just unwrap it directly. I don't know if I did the implicit unwrap and then the question mark one or something. I don't know. All right, let's see if I've got the syntax correct. Okay. Now my argument is we've already covered all these cases and you can't get there, and that this should be equivalent. It's still ugly. but it works. That's a virtue. I think I can fold these like this. Maybe that. All right. All right, so if they're both integer values, use it directly. If they're float values, if the left-hand side is a float value, fine. If not, force it to 1 or error. Same thing for the right-hand side, then just return their sum. But if either one was a weird type, then blow up. Okay. Well, our pace is slower. We didn't really deal with this complication like in the spike, right? We just returned 42 and didn't do the addition. So here we are paying for all this. Now, I want to refactor some more. The challenge I see is there's a number of functions, there's plus and times and divide and whatever's that are going to be exactly this structure. And so I want to make a function that you give it two expressions and a combining function for ints and a combining function for floats. Is that going to do it? Well, let me write an assertion, I guess. Okay, so that's sum. I guess what I want to say is we got a test and it's, I don't know what we want to call it, compatible or force. What do you call those conversions? And they're implicit type conversions, joint types. Joint. Well, no, I only want two. Okay, what's this going to do? Joint. Join. Convert. I don't know what words I got here. Convert, compatible. Oops. Convert, compatible, join, joint. Convert, maybe numeric. All right, so, well, what I'm thinking is if you give somewhere you're going to call numeric, and we want to get back a function of two arguments. That takes expressions. I don't know. I'm getting myself balled up here, but I think what you want to do is you want to say numeric of sum with $0 plus $1 and $0 plus $1 one of them is integer, one of them is numeric. This is a function, and it gets you back a function that deals with all this stuff. And if I call function of integer value 2 and float value 3.0, that thing should be 5.0. Result, I guess I gotta, should be float value 5.0. Okay, what have I got? A compile book somewhere? Let's see if I can pull the term I want from this. Lexical analysis, syntax analysis, type checking, type conversions. I had convert. Okay, let's see. I don't think I want the sum here anymore. I just want this. Okay, I think. So you call convert primitive functions dot convert. It's a little annoying. You call convert on two functions, and it gives you back a function of two arguments that returns an expression. I don't think I can tell. Yeah. Until we define this thing. So let's define this thing. Static function convert. All right. It's taking an integer function. So this is, we'll call it convert2. I may be speculating here, but convert2, it's going to take an integer function, int producing an int, and double producing a double. Okay, those are the two functions we're passing in. And then it produces some other horrendous function we'll get in a moment. Okay. It's going to produce a function that takes two expressions and produces an expression. Okay, put this all in blocks like that. Not really needed, I don't think, but maybe clearer, I hope. Okay, so the first function convert gets is int to int. The second is double to double, right? So the two ways to plus, to add. And the result is a function that takes two expressions and returns an expression. So this is a replacement for sum. After all that work, yes, I know. Okay. And so I think we can let's make sure this works. Okay. Oh, we got to return something. Oh my gosh. Well, we need an expression that we need something like this. And I'm just going to make one up. Sorry. Okay. It calls, let's see. We'll call it useless. Return useless. And useless is returning X. Okay. So, not totally useless, but it'll get us through. All right. I'm just trying to compile and fail. But first compile. Unnamed parameters must be written with empty. Okay. I guess that looks better. And int goes to int, double. Double goes to double. Okay. Unnamed parameters must be written with the empty name. Oh, this is our int function. Of this type. Oh my goodness. These functional functions can really get you. Double function of this type. Okay, so 2 arguments. One's an int function, one's a double function. I don't think I need to have these then. I glommed onto the wrong part of the message, I think. Int int goes to int, double double goes to double. And it should fail. Should run, but fail. Okay. Huh. 2 is not equal to 5.0. So it did get the first value back. All right. Can I change this to make it easy? Let me duplicate some tests. This is int plus int. And I'm going to make this original. Okay, so I've got some primitive. Did I get braces messed up? All right, I have some primitives. Int plus int, float plus int plus float, float plus float. Those are the ones I want. Some primitive non-numeric. Okay, I want everything to pass except that last test. They're all copies. Shouldn't be an issue. All right, now I want to change. I'm going to make all these use the same test. Do I want to do that? Let's just tackle. Oh, golly. Let me take them as a block. I don't do this very often, but convert to takes x plus y, int function and double function, x, y are not. Oh no, that's okay. We want to take the function we get back, convert that, and apply it to x and y. I think that's reasonable. I mean, it's odd, admittedly. I don't know if it'll make me take an extra step. 1 is not equal to 3. Okay, that's fine. Yeah. So we're doing the right thing. Okay. I don't know if you look at it as readable. Let's pull it out as a result anyway, and hopefully that helps a little. Let result equal that. And here result. Okay, so if you call convert to with an int function and a float function, and then take whatever you get back as a function and call that function with the two values, we should get a properly typed, properly valued result. Okay, I'm going to keep this just because we're using plus consistently. And I think this line should stay the same. And we'll deal with the last one last, I guess. Okay, so that failed. Convert to. This should be result. Yeah, I'm feeling like I could have done a better job of getting there. But I'm going to get a bunch of failing tests, and then we'll make them all pass as a block, I hope. Okay. Now we should have 5 failing tests if I counted right. The 4 variations and the convert numeric, but we haven't dealt with this one. Okay. All right. So again, it's time for a break. So we'll take 2 minutes. We'll come back, see if I can make this swap in this sum function and make it work for our case. So we'll see. 2 minutes. So what the situation we have is we've got this sum function that does all the work about figuring out whether it's int or float and what to do about it. It implicitly uses the plus here and here. This one's an int plus, this one's a floating plus. And we have convert to that we would like it to do basically the same thing. So I'm going to grab all this, the body, and instead of useless, okay, I'll do that. Okay, so now here, instead of calling x plus y, I want to call int function of x dot value and y dot value. All right, and then down here correspondingly, double function of LHS value and RHS value. Okay, and these things should work. I'm leaving this here for now, but I think all our tests should pass. If they don't, then I've taken too big a step, and it looks like I've taken some syntax errors here. I don't know what 9 and 5. Oh. Yeah. Can I do this way? Oh dear. Okay. This. I want to return a closure, which is a function basically x and y in all this like that. Okay. So I'm returning a function, so I got to return some sort of functional kind of object. And I call them int function, double function. All right, let's try building again. Oh, no. Oh, you got to spell it right. Okay. Oh, I got to say escaping here. non-escaping parameter. Okay. See if I can get the syntax right. Oh. Apparently not. Okay. Try one more time. Yeah, it's just I haven't done enough with these escaping types and worrying about these closures and all that. You know, it really is closer to a functional style. And in functional languages, lots of times they deal with all this for you, but you have to be a little more explicit here. All right, but our test did pass. Yay. All right, let's convert this last one. We're going to call the same function again. Result is primitive function convert applied to x and y. And here we want result. Okay. Saying that if we did the conversion right, if you pass in something with not both types not numeric, here we have only one numeric, then this thing should give you an error message, can't happen. All right. And I don't know why I didn't convert that before, but it should pass. Okay. All right, now we can refactor a little. Let's push. I haven't done that for a good while here. All right, so we added a sum method that takes types into account. And a convert method that converts Swift numeric functions to expression functions. Okay. Now I'm going to refactor a little. All right, so convert to, I can live with the name. I mean, it's a little clunky, but I think if you follow it through two integers, yes, call the int function. Something that's not a float, convert it to a float. Same for the other argument, and call the double function if you can, or return an error. Okay, so useless is no longer needed. It was just there to get a legit return type there. I probably could have just passed in a, closure with $0 in it or something. That is easy. All right. Now we got the sum function. I don't really think we want sum. Okay. For all the work we did on it, it really was a good stomping ground for the work we needed to do for convert. So I can do that, and I'm going to take those tests out. That's those original tests. All right. So I don't know. It felt like it made us smart enough to be able to do the second thing. Maybe I'm projecting. Okay. These should all pass. Now, I haven't used Swift enough to know what's legal here, but I feel like in Java, I think you could probably just pass the plus by itself. Let's try that. Plus plus. Are you going to work? Yes. Okay. It's a little cryptic, I guess. I don't think it's any worse than this. Let's change all these. Plus and 1, 2 more. Okay. This test is an integer plus a float. I think we have that. Int plus float, right? So that test was redundant. It got us started on the convert. Okay. Is this really some? I guess it's okay. All right. Okay, so the nice thing here is what I feel like we can do is any simple numeric operation that takes takes ints or floats and reacts this way to the combined type, convert to takes care of it. And you just pass the functions in, an int function and a double function. That feels good to me. Somewhere we have to define what our functions are, and maybe this thing should do that. That kind of is the way that native class worked, right? That it had the list of operators. I think what we're going to say then is static let operators, prefix operator primitives equal something. And what I want that to be is an operator mapping to a function. So I want stuff that looks like that. All right. And where are our functions? We had a list. Let's get all those binary operator functions. Now these two less than, or equal, I don't know if those are defined for custom values. We still have Elm REPL. Is false less than true? No. Okay. It's not. So it sort of fits our mold, at least for the types we have. We don't have string or character types yet. Okay, so plus, that's a string operator. That's a Boolean function, generic function, less than and minus is numeric. All right. And this, I don't normally test stuff like this. It's just a list of things. That I don't feel like it adds anything really. We will test them in their usage later, but just being a list, I don't think it's enough for me. So let's see. We need these 4, and then we had a couple more operators. Yeah, percent times that equal. Well, for our types we have, it's okay. This one is not. This one is. Those don't apply. Okay, so what have we got? Keep saying that. We certainly have these. That's booleans. Function stuff. Okay. Primitive functions. I'm just pasting it in here for the moment so I can quit going back and forth. These. Equals yes. So far, that will change. Slash and not equals. Okay, this is pure int. Okay, they'll need another approach, but that's okay. All right, so this one. Crazy. Like, how do I know it's not a template? I hate to think of the parser that tries to decide that. Now I do have to use the same operator 3 times, or sort of the same operator. I don't know if that means the same thing in Swift. Less than, or equal, greater than or equal. Let's see. Pow. Is double to double. Okay. That is XOR in Swift. Okay, star. Equals. It does seem a little weird to write them that way, I grant you. Okay, so we got percent, star, equals, not equals, and slash. All right, let's get our numeric ones together. Plus, minus, times, star. I guess I can. And a greater, less than, not equal. Okay. All right, we'll come back to those. I'm seeing it's getting late on today. All right. This is good, or good for now. I think this stays. We may find a better way to convert between types and stuff like that, but this'll get us for now. There's some logic to the ints and the floats and the numerics that I haven't quite pulled out in my head, but it's okay. Next. Well, let's take this list, put it in our to-dos. I guess I wasn't very good about that today, was I? Got random stuff there. Prefix operators. Okay, that's kind of what we're doing. We got a lot more stuff going on. Story operators. Haven't been keeping up. 25th. Oh, yesterday was a spike all day. All right, so story, we deleted this. And we haven't done curry. I think we'll get that in a moment here. We haven't dealt with those. Okay, but what we did was, this is a refactoring. We defined primitive functions with a convert_to method that takes int and float versions of a function and wraps them into a function compatible with the interpreter. Something like that. Okay. And I think next let's deal with this curry function. It's kind of on those lines in a way, and I don't know where it belongs. Okay, so that's another factor. Well, I think it probably belongs in our type. Let's push this. I think we're green. No, we're not. What have I done? Left out a comma. Cannot convert double to wool. Oh, those are not that type, are they? Okay. Yeah, they don't yield the same type. Okay. Am I allowed to have this comma? Oh. Oh, and we said there was... Wait, I left out one. Yeah, that's why I argue we don't need tests. It's... Oh, is that all? I'm going to leave this TBD. We don't know how to make this work. Going to leave this TBD. Yeah, I mean, gosh, it's kind of speculative stuff, isn't it? Don't do that. I want the example because we do want to get back to it. I think it's okay for these because they are relatively well defined in both languages. These just act a little different. This may only be an int function. I don't know. We'll see. But we're green, so we'll commit. We've got primitive functions. Convert_to converts a swift int and double functions into a 2-argument function on expressions handling int float type conversions. I think that can go. Okay. Now this lovely curry function we had. Well, you can see we've got our convert_to that replaces this. All right, so we're trying to write a function. I'm gonna copy this. It's somewhat, well, let's see. I'm gonna move this alphabetically. Where'd it go? Primitive. Okay, now I want a primitive type. Let's put that on here. Test first. Okay, primitive tests. We'll rename this. Okay. And this should fail. Okay. So our test is curry produces, well, turns 1 2 argument function into 1 argument function. Okay. Can I do that? All right, and the test is something. Well, we're talking about primitive.curry. Now, this is where we're using convert to plus plus. All right, so convert to gives us a 2 argument function. And we're getting a 1 argument function back. Hey. Oh, Frank Tech. Okay. Didn't read right to my head for a moment there. Okay, so we're trying to call our primitive curry function, give it a function, and it returns back a function. I don't know if that's enough to get us completely satisfied. Convert to primitive. Okay, so we're messing around with these functions returning functions, and it literally is a mess. But we're going to define a curry function that you give it a primitive function. Convert to gives it a 2 argument function that takes expression, returns expression. We're wrapping it up so that you get a primitive function that does the same thing. Okay, so what am I expecting back? Well, I think if you call 1 argument, well, let's call this 1 argument function. Function of integer value of 3. Okay. You should get back a function. I think you should get back a primitive. I don't know if we have to apply things twice, and we don't have the mechanism for that. So this may be a premature test. Okay. Maybe this is function 1. Function 2 is function 1 applied to integer value 3. What did I do? Oh. If you apply this to integer value 3 plus, and then you let the result equals function 2 applied to integer value 4, then we should get back result should be integer value 7. Okay, so primitive.curry is not defined, but if you pass it a function of 2 arguments, expression goes to expression, it returns a function of 1 argument. Expression goes to function that takes expression, returning expression. So if you got a function 1 takes 1 argument and it returns you another function, and you pass the second argument, you evaluate it, you should get the right result. This feels like a big step. We're going to put the primitive class in though. And we may pause that the work on this particular test and take a smaller bite, but let's add primitive, just a Swift file. Okay, I'm going to rename it. Failed to rename. Okay. Okay. Everybody agrees it's a bad name. Primitive. Did I spell it right? Something must be there. We'll live with this. I'll fix that one offline. Okay. But we got class primitive. And we want to be a, well, we don't know what we want to be yet. We do. But I'm just going to, that's where we're headed. And this, and we're just trying to get this curry function in. All right, I will copy that and we'll paste it, but our implementation is not legit. Okay. Missing return. I don't know what we can return there. Well, I guess we can return something like this. Lambda x goes to variable x. And I think I have to put this in brackets. Nope. Okay. So I'm supposed to return, well, it's got to be an expression, but it's really supposed to be an expression goes to expression function. We're not saying that because we're in this interface between the primitives on the Swift side and the primitives on the Elm interpreter side. We're trying to kind of an imitation of the native functions in Elm that defer to JavaScript. We're trying to get ourselves from the Swift functions like plus, actual plus operator in Swift, up into the function domain on this side. All right, this test should fail. I'm very confident of that. Well, not if you... Okay. Yeah, we have to apply. So I'm gonna comment that. Let's make sure this just even compiles. Okay. That's okay. We'll pick up there. All right. So we will pick up there next time, which is Tuesday, 1 to 3 p.m. Let's see. We're still in April, right? So 23rd, 30th. So Tuesday the 30th and 1 to 3 p.m. Eastern time. we'll pick up with this and get this curry function working. And I think getting that working will require us to get the rest of the primitive working, and if we're going to make these function calls work. They won't work in the position they're in now. We'll have to do some converting back and forth from the expression world to ours. Probably have to call expression.apply or something. Okay, thanks for joining, and I will catch you in the future. Bye-bye.